Hello, hello, hello. This is Coach Ikram and welcome to this video on individual gas laws. In this video, we're going to discuss Boyle's law, Charles's law, and Gay-Lussac's law. So we're going to kick things off with Boyle's law. Boyle's law discusses the relationship between pressure and volume when your temperature is held constant. And it's notated by this equation right here. P1 V1 equals P2 V2. And Boyle's law states that as pressure increases, volume decreases. And as pressure decreases, volume increases. This is going to be an inverse relationship between pressure and volume, which should make sense when you look at it algebraically up here. Visually, if you look at it, you've got a piston over here on the left-hand side. It's got a pressure of 100 millimeters of mercury, and it's got a volume of 1 liter. If you notice on the right, we have increased our pressure by 2, times it by a factor of 2. So now we have a 200 millimeters of mercury of pressure. Therefore, our volume has been decreased by half in that inverse relation. If you look at it graphically, if you graph pressure versus volume, you're going to end up with this inverse curve right here. But if you graph it, because it's an inverse relationship, if you graph it volume versus 1 over P, the inverse of P, you're going to end up with this positive slope. And that just gives you a good graphic representation of Boyle's law. So like I said in the previous slide, we're going to use P1 V1 equals P2 V2 as our Boyle's law equation to solve for various variables. So in this example, it says a high altitude balloon contains 30.1 liters of helium gas at 103 kilopascals. What is the volume when the balloon rises to an altitude where the pressure is only 25.4 kilopascals? So I'm going to plug this into P1 V1 equals P2 V2, and I'm going to solve for my new volume. So my givens are 30.1 liters of helium gas. I've got a pressure here of 103 kilopascals and a new pressure of 25.4 kilopascals. So my equation is P1 V1 equals P2 V2. My original pressure was 103 kilopascals. My original volume was 30.1 liters. My original, my new pressure, is 25.4 kilopascals. And I don't know my new volume, so I'm going to leave that as the variable V2. Now I'm going to rearrange my equation and divide both sides by 25.4 kilopascals. Note that my kilopascals cancel on the left, and I'm left with liters, which is what I'm looking for. I'm going to solve the algebra, and I'm going to get V2 equals, with 3 significant figures, 122 liters. And that is my new volume. And this should make some sense. If you look at your original equation, your pressure is cut by about a factor of 1/4. Goes from 103 down to 25.4, 1/4, which means that your volume should quadruple. And if you look, it goes from 30.1 to 122. So that makes sense. It's a reasonable answer to what the problem is asking you if you understand the concept of Boyle's law and that these are inverse. The next law is Charles's law. Charles's law is the relationship between volume and temperature when your pressure is held constant. So in this case, we're going to be using the equation V1 over T1 equals V2 over T2. So Charles's law states that as temperature increases, volume also increases. And then as temperature decreases, volume decreases, which means that this is now a direct relationship. So if you notice here, we've got a piston over a heat source, and as we heat it up and we're increasing that temperature, our volume increases because the gas moves faster, kinetic energy increases, the gas particles move faster, and therefore if it's a flexible container, the volume is going to increase. And remember, pressure is held constant, so in this case we are dealing with flexible containers. The relationship between volume and temperature when the pressure is held constant is direct. And so if you look on this graph, you'll see we've got volume in a different language, but you can still read it. Volume versus temperature, and you'll see that it is a positive. All right, let's go ahead and do an example of a Charles's Law application problem. Example 1 says a balloon inflated in a room at 24 degrees Celsius has a volume of 4 liters. The balloon is then heated to a temperature of 58.0 degrees Celsius. What is the new volume if our pressure is held constant? So we have our equation for Charles's Law, which is P1 over T1 equals V2 over T2. We have our original volume, which is 4.0 liters. Our original temperature is 24.0 degrees Celsius, so we have to go ahead and convert that to Kelvin because all of our calculations have to be in Kelvin with temperature. So 24.0 degrees Celsius plus 273.15, and rounding for addition and subtraction significant figures rules is going to be 297.2 Kelvin. So I'm going to go ahead and plug that in, 297.2 Kelvin. We do not know my new volume, so I'm going to leave that as my variable V2. And then I'm going to plug in my temperature, which is 58.0 degrees Celsius. Again, I have to convert that to Kelvin. So 58.0 plus 273.15, and I get 331.2. Now I'm going to cross multiply and divide to solve for V2, and I got V2 to be equal to 4.46 liters, and that is 3 significant digits. The final law that we're going to talk about is Gay-Lussac's law, and his law discusses the relationship between pressure and temperature when your volume is held constant. So his equation is P1 over T1 equals P2 over T2. So here you're talking about pressure and temperature. Your volume is constant, so we're not worried about it. Pressure and temperature, as temperature increases, pressure also increases. And as temperature decreases, pressure decreases. And remember, all of this is in a fixed container where your volume is not going to change. And this is also a direct relationship. So you should see some algebraic similarities between this law and Charles's law. They're both direct relationships, and so the algebra looks very similar, as it should. And looking at it graphically, you should also notice some similarities between this law and Charles's law. We've got pressure versus temperature here, and it is a direct relationship. As your temperature increases, so does. So let's go ahead and do a problem with Gay-Lussac's law. It says a gas is left in a used aerosol can at a pressure of 103.0 kilopascals at 25 degrees Celsius. If this can is thrown into a fire, what is the pressure of the gas in atmospheres when its temperature reaches 928.0 degrees Celsius? So I'm going to go ahead and plug my numbers into this equation, starting with pressure number 1. So P1 in this case is going to be 103.0 kilopascals over 25.00 degrees Celsius. And remember, I have to convert that to Kelvin by adding 273.15, and I get 298.5 Kelvin. Then my new pressure we're not sure of, so we're going to make that P2. And its new temperature was 928.0 degrees Celsius, so I'm going to add 273.15 to that. And I get 1201.2 following significant figures rules. Rearrange, and I'm going to solve for pressure, and I get P2 to be unrounded 414.971 kilopascals. Except my question asks for my pressure to be in atmospheres. So I'm going to go ahead and convert by setting up a dimensional analysis problem. Or 101.3 kilopascals for every 1.000 atmospheres. Cross off my units, convert, and I get 4.096 atmospheres, and that's to 4 significant digits. So now we're going to touch on a final individual gas law, and this gas law doesn't have a name, but it's the relationship between pressure and the number of moles. And it states that if the temperature and volume are constant for gas, then the pressure of that gas is proportional to the number of moles of that gas. And it's designated by this equation, P1 over N1 equals P2 over N2. So let's go ahead and use this equation in an example. Because a student has a rigid container at a pressure of 745 millimeters of mercury, containing 1.23 times 10 to the third moles of hydrogen gas. It's held at a fixed temperature. If she increased the number of moles to 4.78 times 10 to the third, what will the pressure be in atmospheres inside that container? So I've got my equation, P1 over N1 equals P2 over N2. My original pressure is 745.0 millimeters of mercury. My original number of moles is 1.23 times 10 to the third. I don't know my new pressure, but I do know that she increases the number of moles to 4.78 times 10 to the third. So when I rearrange and solve for P2, I got P2 to be 2,895.2. I'm not going to change sig figs until I do my next step because that's in millimeters of mercury. And I need to convert that to atmospheres. 2,895.2 millimeters of mercury. 760.0 millimeters of mercury is equal to 0 atmospheres. And then when I convert to 3 significant digits at the end, I get 3.81 atmospheres. But even if you hadn't converted to atmospheres, you can still see that our pressure, when you compare the millimeters of mercury in this answer to the millimeters of mercury here, because you're adding more number of moles to your container, your pressure has gone up. That is the end of this video. Make sure you have taken good notes and come to class with questions. Thanks.